Hello, everyone. Welcome to this week's Green Bank Community Zoom. Just a couple announcements before we get to the talk. So we are in the midst of our summer shutdown and we're working on the foundation of the Green Bank Telescope, and we're replacing a section of foundation that shows some degradation. They're busy jackhammering away. You can see daylight through the foundation. The good news is that this portion of the foundation seems to be in much better shape than the previous portion of the foundation that we worked on. So the repairs may not be quite as extensive as before. The area is a bit larger, but the depth will be a bit smaller. So that's all working very well. We expect to have that done in a few weeks, and we'll get back to operations end of September. We're also working on an upgrade to the ultra wideband receiver. We're building new ridges. So there's a new design for the ridges that go along the feed horn, and these ridges are optimized so that the performance across the frequency range should be better. At the moment, we have a bit of a issue where there's a low sensitivity part of the spectrum. Well, actually, we switch E&M modes at that frequency. The new ridges should obviate that problem, and we should have a much better performance all the way through the entire frequency band. So we'll keep you posted on that. So with that, I'll hand off to Jay Lockman, who will introduce today's speaker.
Thanks, Jim. Today's speaker is Thomas Krichbaum from the Max Planck Institute for Radio Astronomy. He'll be speaking to us on mapping the jet origin of M87. Let me remind everyone that this webinar is being recorded for future viewing. And if you have questions, please submit them through the Q&A button on the bottom. Okay, you can take it away, Thomas.
Okay, thank you. I will share my screen. So can you see? Can everybody see?
Yes.
Good. Okay, I'm Thomas. I'm a member of the VLBI group of the MPIFR in Bonn. And I thank you very much for the opportunity to present our new results for the M87 radio galaxy from the 3 mm VLBI observation with the Global Millimetre VLBI Array. This work, of course, was done by a lot of people, and for those interested in more of the details, I would like to refer you to the recent publication in Nature. I also would like to emphasize that this work is really based on the contribution and on the strong efforts of numerous people, all eager to push VLBI to the highest possible frequencies and resolution. So let us start now. The origin of a jet is still a topic of scientific debate, and a main motivation for VLBI observations in the millimeter regime comes from the wish to image the central region in our galaxy and also in distant galaxies with the highest possible spatial and angular resolution in order to better understand how black holes accrete matter and how black holes expel those powerful jets, which we all know. Nowadays, there are basically two competing jet formation models discussed. They go back to the original papers of Blanford and Payne, which I call the BP model, seen on the top left panel, and also on the Blanford and Snag BZ model. Some more modern variants of those models exist, but the principle behind these modern models is still the same. The BP model uses basically a magnetic field which is anchored in the rotating accretion disk, and it consists of helical and it consists of colloidal and toroidal components, and the matter, the particles are accelerated into the jet via a so-called magnetic slingshot process. While the BZ model extracts rotational energy in the ergosphere directly from the black hole spin. So in this case, the accretion disk does not play a strong role, and the jet is launched directly from the black hole through electromagnetic forces. In the BZ model, we have two variants which are related to theoretical work. One is the so-called magnetically arrested disk variant, where the disk is highly magnetized and dominates the energy budget by its magnetic energy. The other variant is the SANE model. SANE stands for Standard and Normal Evolution. It's basically a model which is dominated by the energy of particles, like the ADAF or the RIAF models, which are favored, for example, by Narayan and his collaborators and many other people. One basic property of the BZ model is that you have a more narrow jet and eventually also a faster and more energetic jet, while in the BP model, the jet is much wider. But as we can see, it's not so easy to distinguish between them, and we need a lot of observational parameters to put proper constraints. So let's go now for M87. Of course, you know that the jet was already discovered by Heber Curtis at Lick Observatory in California in 1918 by visual observations. The source is well known at many wavelengths. It is studied over the full electromagnetic spectrum since decades. It's classified as a Van Allen 1 galaxy, and the important point is it's bright enough for VLBI imaging at millimeter wavelengths. That's the main reason why the EHT collaboration was able to publish the first image of a black hole from that source. The source is just close and bright, and the EHT beam is small enough to resolve the central structure, which is currently interpreted as a shadow of a black hole. Now, before I go into this, let me point out some highlights from previous decades of millimeter VLBI observations. Of course, you all know the famous work by Craig Walker and his collaborators who did the VLBA movie, and which show that the motion is subluminal and that the jet is edge-brightened. I like to remind everybody on a paper by Hada in 2011, who did the core shift measurements. And from these core shift measurements, we know already that the jet apex is separated by about 10 to 20 Schwarzschild radii from the black hole. More recent measurements with the GMVA published by Kim et al. Show this V-shaped structure, and already also showed, and you see that in the slide on the bottom right, some evidence for a central spine. And finally, advanced imaging applied by Mertens et al. In 2016 showed that indeed there are fluid vectors along the jet ridges and also in the spine. M87 may be called Rosetta Stone for studying AGN engine because the combination of its relative proximity and also large black hole mass makes it really ideally suited for high spatial resolution VLBI imaging in the millimeter bands. And so we can study not only the black hole, but also the jet launching and how black hole and jet interact. At a distance of about 16.8 megaparsecs, the Schwarzschild radius for a black hole of 6.5 billion solar masses is about 7.6 microarc seconds, which means that the expected black hole shadow, which is just the square root of 27 times that number, is of the order of 40 microarc seconds, so is in reach for global millimeter VLBI imaging. The 3 millimeter VLBI imaging done with the HSA and with the GMVA in the past traces the jet down to a few, let's say 5 to 7 Schwarzschild radii scales. Typical beam size of GMVA observations is 50 microarc seconds. 1.3 millimeter VLBI revealed the first image of a supermassive black hole because its beam size is now only 20 microarc seconds, and so one could see the ring, which has a diameter of roughly 5.5 Schwarzschild radii. In contrast to Sagittarius A star, which is also close by and for which a black hole ring could be detected or was detected and published recently, the advantage of M87 is that it's varying on a much longer time scale. So ISCO time scales are of the order of 5 days to 2 weeks, depending on black hole spin. And so one can integrate longer, and also the aperture synthesis imaging is less affected by intrinsic source variability. While for Sagittarius, the source varies a lot already during an observing night. So the motivation for new GMVA observations basically came from the fact that ALMA is available as a phased array and can be used at 3 millimeter and at 1 millimeter. And with the addition of ALMA, one could overcome a limitation of previous imaging, namely the relatively elliptical beam of, for example, the 2018 observations, where we have a very good resolution in east-west direction, but a not so good resolution in north-south direction. I would like to mention that even for non-ALMA imaging, the big telescopes play an enormous role, because with a correlated flux of about 0.1 Jansky on the longest baselines, one really needs the GBT, and one needs the IRAM dishes and the Effelsberg dish to detect the source when the visibility goes down at the very longest baseline. As you know, the previous imaging at 1 millimeter did reveal the black hole shadow, but there was a lot of missing flux. So the 1 millimeter image has about half of a Jansky of missing flux, which cannot be imaged due to the relatively sparse UV coverage of the EHT. And GMVA, with a larger number of stations, but of course observing at a slightly longer wavelength, is in principle able to see black hole and jet, however, not with the sensitivity of the past. Therefore, we decided to perform new GMVA observations, and this time combining the GMVA with ALMA, the phased ALMA. In this particular case, 47 dishes were phased up. And in addition, also, we had the first time the GLT, which is the Greenland Telescope, which is a telescope located in Thule at the moment. So the total number of stations which observed on April 2018 was 16 stations. The European stations, Effelsberg, Onsala, Metzahovi, Jebus, Pico, Valletta, the GLT, then the GBT, and 8 VLBA stations and the phased ALMA. And the recording mode was at that time 2 gigabits per second. Nowadays we could do better. We have 4 gigabits per second. And the correlation was done with the DivX zoom mode at the MPIFR here in Bonn. The figure here shows the UV coverages of our calibrators and also of the M87 target. In the UV coverage, you see the red symbols, they denote for the ALMA baseline. And the orange symbols, the yellow symbols denote for the GLT, Greenland Telescope baselines. So as you can see, with ALMA, we can improve the north-south resolution by a factor of about 4 for M87. So the typical observing beam then is 40 to 70 microarc seconds, which translates into 5 to 9 Schwarzschild radii at the distance of the black hole of M87. Now here are the imaging results. In the top row, you see from left to right always the same data set, but the imaging just done with the VLBA and the GBT. The beam size is 0.6 times 0.13 milliarc seconds at 3 millimeter. Then when we add the European stations, we reduce the beam size by about a factor of 2. And now adding the GLT and ALMA gives a beam size of 73 times 40 microarc second. And this new image shows an edge-brightened fan-like structure. And if we zoom in into that and convolve the map with a circular beam, which is equal to the minor axis of the elliptical beam, we get on the bottom right the image of the central region. I'll come to that in a moment. For comparison, I also show in the bottom row an HSA image published by Hada et al. based on 2014 observations, and a GMVA image published by Kim et al., which is a stacked image of 5 different GMVA maps, which are separated by several years in time. Now let's go a little bit more into the details. So these new maps here show again the limb-brightened structure, which was clearly seen already earlier, but now with better fidelity. There's a very wide jet opening angle near the core, and there are some bright spots which seem to be located at the base of the northern and the southern limb. And these hotspots are separated by about 180 degrees. However, some testing also showed us that at least some of this hotspot structure may be also due to the UV coverage. So not everything which we see here may be 100% real. So the azimuthal structure, which I will show later in the ring, is also suffering from UV coverage effects. On the right side, you see the same map, zoom in, but now convolved with a 37 microarc second beam, and you can clearly see here this structure at the center. There is no counterjet visible in this map, and the central spine, which is seen here, is still not 100% robust. So we do believe that there is emission in this region, but it's only that 50% of our image reconstructions showed it, and it's not unique, and it's definitely a factor of 2 or so fainter than the outer two edges of the jet. The core region is clearly resolved, and there are hints for a structure which looks crescent-like. In order to test this and to get images of somehow a higher resolution, we applied Bayesian imaging methods using regular maximum likelihood methods to give us a factor of 2 or so better resolution than clean can give. In particular, we used the so-called SMILEY imaging software developed by Akiyama and his collaborators. SMILEY stands for Sparse Modeling Imaging Library for Interferometry, and it uses sparse sampling techniques and other regularization methods. The maps shown here are shown with some sort of, you would call it, different weighting. So we changed the total square variation regularizer. And we can see that depending on the choice of this regularizer, we can sharpen the image or blur it a little bit more. So the important point is that all SMILEY images confirm the ring-like structure already seen in the super resolved clean images. And we see a central depression whose depth is a little bit depending on the choice of the regularizer TSV. And as I said before, the azimuthal details of the ring structure should be interpreted with caution, because there are also effects which are related to the UV coverage. So now here is the zoomed in version where we combine the jet and the ring structure. The bars show linear scales of 50 microarc seconds for the ring and 500 microarc seconds for the jet. Just to remind you that 50 microarc seconds correspond to 4 milliparsecs, or in other words, 4.7 light days. So the bar here is 6.5 Schwarzschild radii long. And for the ring diameter, we find that the diameter itself is about 8.4 Schwarzschild radii, but I come to that in a moment. In order to not only rely on images, but also look at the visibilities more directly, here we plot the visibilities of the EHT observations at 1 millimeter on top, and the GMVA observations of this observation here on the bottom. The red arrow here marks the location of the minimum, and by applying the simple formula, we can estimate the diameter if we assume a very thin ring model. Thin ring means that the ring has no width at all. And with that simple formula, you can get a first idea about the size of this ring. So for the minimum at 3.4 gigalambda seen at 1.3 millimeter, we get a size of a diameter of 46 microarc seconds, and from the GMVA we get a diameter of 68 microarc seconds. In order to further test the idea of a ring, we applied now different model fits. We've chosen a simple Gaussian point-like distribution, a uniform disk, a uniform sphere, a thin ring, and a thick ring. These are denoted by the different lines with different colors. And the area here circled in red is basically all, these are ALMA baselines. So we checked before doing so, before doing the model fit, we checked very carefully also with the calibrators that we have no systematic offsets for the ALMA station. And we applied gain transfer methods from 273 and 279 to M87 and vice versa to be sure that this rise in the visibility beyond the first null is real. And from our fitting, which includes fitting to the visibility amplitudes and also to the closure quantities, we concluded that a thick ring model fits the data best. So this is a visualization of the fit here. We plot the chi-square versus the diameter for the inner and the outer radius of the ring and for the central portion of the ring. And this is the best fitting model here, which is this model marked by a red quadrat. So we also conclude that the width of the ring is about 22 microarc seconds, is favored by the data. However, if we now compare, well, I cannot proceed. Now, if we compare different maps and models obtained from fits to the data where the jet is included and fits where we subtracted the jet, this orange is jet subtracted data, we see that the diameter which we get out does not depend much on the jet subtraction. However, the width of the jet, of the ring, depends much more on the jet subtraction. So in the paper, we were very careful and we just said that the width of the ring is not so well constrained. It's probably larger than 20 microarc seconds. Best width which we get is somewhere between 30 and 40 microarc seconds. Now, if we compare the property of the ring, in particular diameter between the 3 millimeter and the 1 millimeter, so the left panel shows with a solid circle, shows the 3 millimeter diameter, and on the right panel with a dashed circle shows the diameter at 1 millimeter, and we transfer this dashed circle over here. So this map shows both the 3 millimeter and the 1 millimeter. I hope you can see my cursor. And the ring diameter at 3 millimeter is 64 microarc seconds, plus minus these numbers as denoted there. And at 30 gigahertz at 1 millimeter, the ring diameter is 42 microarc seconds. So the ring is much larger, by about 50% at 3 millimeter than at 1 millimeter. Since the data were not obtained simultaneously, you can see the maps are from 2017 here and 2018 here. We also were a little bit worried if source variability could cause such a difference in the ring variability, in the ring diameter. However, when we checked for the total flux density variation of M87 between 2017 and 2018, we found out that it's less than 20%. And the bottom panels here show how the ring diameter at 1 millimeter depends on observing day in April 2017. So we see almost no variation of the ring diameter over days. And recently, Vilgus et al. Also published a paper where he model fitted earlier 1 millimeter data, and he also finds that the ring diameter is somewhere between 40 and 45 microarc seconds over many years. So we think that the ring diameter is not sensitive to time variability, and therefore we have to worry if what it means to have observed a larger ring diameter at 3 millimeter than at 1 millimeter. Another important point is that we looked at the transverse width of the jet. So here we plot the jet width as a function of radial distance from the black hole. The red data points mark the new data obtained from this experiment. The gray data points are from earlier observations. In region 2 and 3, red and earlier data overlap, and we see the classical well-known parabolic jet profile, which goes roughly with z to the 0.6, so it's almost quadratic. However, if we approach the core region at distances below 0.2 milliarc seconds, we see that the jet width is larger than the back extrapolation of this parabolic jet profile, and is also larger than the theoretically expected jet width of a BZ jet. So the gray area here marks a theoretical simulation of a BZ jet, and we see that the BZ jet also has some sort of slightly larger ring diameter, but we observe something which is definitely larger than the BZ jet. And this makes us, of course, worry what could that be. And this is certainly a topic for future research, in particular for more detailed theoretical modeling. We applied a very simple model just to test some very basics. In the paper, we used the GRMHD modeling, where we tried to model the flux and the image morphology of the horizon scale structure, assuming emission either dominated by an accretion flow with thermal electrons, which is shown in the panels B and E, and also by emission from a jet with non-thermal electrons. So the basic idea is you have a jet which is launched magnetically and surrounded by an accretion flow which is dominated by thermal electrons. And for a thermal distribution, the model predicts the right size and the right flux, both at 3 millimeter, and 1 millimeter. So the thermal distribution really fits the data very well, while the non-thermal distribution, which is shown here on the right, fits the data at 1 millimeter, but underestimates the size of the 3 millimeter ring. So this is the blue circle, which is here the same in all the images. And as you can see, the reconstructed simulated image shows a much smaller ring diameter. So we conclude that the thermal accretion model can fit both the flux density and the ring diameters at 3 and 1 millimeter, while the non-thermal model overpredicts the flux at 1 millimeter and does not fit the ring size. So a possible interpretation, of course, comes now through theoretical work, and there are these famous papers by Hardy, Mizuno, and Nishikawa in 2007, who already investigated how how a jet launching depends on a black hole spin. And in these plots, they also have a disk wind and a jet, and it looks like as if the disk wind gets more pronounced when the black hole is rotating faster. And a similar, more advanced modeling done by Tchaikovsky 2015, also McKinney and others have contributed here a lot and have developed the theory very well. These jet models, which can launch a jet via the MAD mechanism, also need a disk wind, which emerges from the disk body. So to summarize, I would like to conclude with the following. So the 3 millimeter core of M87 now is resolved. We see clear edge brightening, but in addition to the EHT image, which only shows the ring, we see the connection between the jet and the ring. At 3 millimeter, the ring diameter is about 50% larger than at 1 millimeter. This points towards emission from optically thick plasma, which could be a wind or an accretion flow, which adds to the gravitational lensed ring emission, which is mainly seen in the 1 millimeter image. Near the black hole, the jet is much wider than expected for a BZ jet, suggesting also the presence of a wind, which is associated with the accretion flow. I would like to make a personal notice that in principle, a wider jet can be produced by a BP jet, where the jet formation is driven by the accretion disk. However, in the BP jet scenario, the helical fields have a much different pitch angle, and one would expect a brighter counterjet, which we do not see. So at present, with a BZ model is therefore favored. Future observations, of course, are needed. We could enhance the bandwidth. We could add more stations. In particular, the LMT would play an important role, but also southern stations in combination with Korea, like ATCA, could help to improve the UV coverage to study in more detail the ring and jet connection. And finally, multi-frequency VLBI observations at 3, 1, and 0.8 millimeter would facilitate the study of the spectral and the polarization properties, and that would help enormously to separate the emission from the accretion flow, the wind, and the jet. Maybe this is a topic for the next generation EHT, but perhaps also for the next generation VLA if it goes to high frequencies. Millimeter VLBI monitoring with a higher cadence, not just observing once or twice per year, would also reveal the kinematics of the ring and the jet, and we could then see how the jet is really launched. I think that's all I can say at the moment, and I thank you for your attention.
Thank you very much for a most fascinating presentation. I think it really shows the power of bringing new instrumentation to bear in millimeter wave VLB. We have time for just one or two questions, and we have a question. Is the ring-like structure possibly visualization of the accretion disk?
Well, the ring-like structure is a composition of several effects. First, it is the photon ring, which is just the gravitational lensing of the emission of the accretion disk, superimposed with emission from the plasma, which is also gravitational lensed. So yes and no. So we see emission from the accretion disk, which is lensed, but it's not completely clear how this emission is composed. I mean, it could be a part of the accretion flow, but it could be also part of the wind, and it's not completely clear what we see. At the moment, I would only say, in addition to the just optical gravitational lensing, we see emission from some plasma, which emits thermally.
Yeah, we have time for perhaps one more question, if there is one. I don't see any open questions at the moment. Well, if not, let me thank you very much for your presentation. I just want to remind everyone that this has been recorded, and so you'll be able to view it on the Green Bank Observatory website within a day or two. Please join us 2 weeks from now, where we will have a presentation by Charles Romeo. GBT Mustang 2 achieves a milestone in galaxy cluster studies. We hope you can join us then. Thanks and goodbye.
Thank you.